Okay, so let's continue. We were just talking about determining ideas to improve wetlands efficiency to remove particular contaminants. And one of the things I want to talk about was when we're removing ammonium, the idea that you have to have that oxygen available to then be able to convert it to nitrate. And then once you have nitrate, then you have to have no oxygen to be able to remove it either through denitrification. An alternative is you can have plant uptake. For biological demand, a lot of times you're going to need a lot of mainly just time for things to break down. For sediment, you're going to want plants to be able to settle out the sediment. The same goes for total phosphorus. You have to have absorption sites. And then for bacteria, a lot of times you need actually UV. So this is where those pools come in really handy. So the theory behind many of these equations is microbial growth kinetics. And since you have this breakdown of contaminants that are microbially available, and most researchers agree there's a degradation of nitrogen species in wetlands and in other treatment systems for that matter. And it's considered to be this first order system based on the Monod equation, which is where bacterial growth is based on a limiting substrate. And so this is where you get the C naught, which is the C outlet, is equal to your inlet to the exponent of the negative K, that removal rate constant with your T. Then you can convert it to this graph here, where we've got on your y-axis the log of your concentration out over your concentration in over time, okay? And so the KT is then the negative. If you're trying to determine what your removal rate constant is, for instance, you could determine it using this equation where you have the negative natural log of concentration out divided by concentration over the time, okay? All right. So your time is a time that the water is in your wetlands. Ultimately, it's your hydraulic retention time. That's what the T is standing for here. So for your design methods, there's some alternative newer versions, which is called the PKC star models. And this is where you have your traditional methods, which just popped up, which is where we've been looking at here. But then you also have this P, and this is if you have like tanks in series kind of instance, where you have how many wetland systems your water is moving through. So one of the questions earlier today was, what if you had like a subsurface system that then moved into another system, such as a surface flow system? This is where that comes into account, where you have so many tanks in series, so many different treatment systems that your system is moving through. And so the P is how many wetland systems you have. The Q is going to be your hydrologic loading rate, your HLR, and then you've got your removal constant. This one is here, which is part of how the equation is derived. You've got your concentration at your outlet, your background concentrations with your C star, and then you've got your inlet concentration. So where do these kinetic constants come from? Ultimately, during the mid-1990s, there was an entire wetland database where people were putting in their data and be able to determine what the normal removal constants were. They're definitely temperature dependent though. So you'll have higher removal rates during the summertime and low removal rates during the winter, which is when those subsurface treatments come in really handy, because the temperature in the soil will be much higher than it will be in the air. All of the Cadlick and Knight models require a first order area based constant, and it's similar to a settling velocity, and we'll talk a little more about that in a minute. There was a change in 2009 where they recognized that wetlands are being based on the means of these databases, which is probably not the best method really for extreme values, and this is important when we think of climate change and how more extreme events happen. And so you have like a skewed to the means for these rate constants. So the values of the constant should reflect a percentile of the occurrence rather than just picking the average mean. So these rate constant models are far from perfect, but they're still under development, where a lot of research, including my own research, really focuses on how do we really know these removal values are applicable for different systems. But they're a good first place to start for us to have an idea for the removal capacity of these wetland systems. One note that you will need to do for your design experiment is to determine what your removal rates will be based on, so if you pull data from the tables that I've provided, you'll get this K20, and ultimately it's the removal rate at 20 degrees Celsius. But you will need to determine what your max removal rate is during like summer times versus in the winter times. And this is where this equation here comes in. Ultimately, you have this KT, so that's the removal rate at a certain temperature, equals your K20, which is your removal rate at 20 degrees C, your theta, which is an adjustment factor that's in your tables that I've provided. And then you have your temperature that you're looking at. So that's like if you're looking at 25 degrees Celsius or 0 degrees Celsius, what is the removal rate capacity at that point? And so they'll fluctuate obviously against over season, and you'll have to make adjustments for winter treatment, particularly important for sizing and performance expectations, and if you need to adjust your pipes to make it a subsurface system, because you can actually get it down to 70 degrees Fahrenheit during the winter if you have it to a certain depth in your soil subsurface. But again, you don't have plants, you have to take that into account too. These values that they're mentioning on page 643 is in that PDF that I have available for you on Canvas. So let's, we're going to, the next rest of this PowerPoint is actually going to be where we're going to be moving into when I get back. So all of next Thursday, we'll be doing wetland design calculation examples. And ultimately, this will give you a chance to be able to calculate the size of your wetland and other types of calculations that you'll need for your design. What I am planning to do is likely I will give you all a few examples for us to do in class, and then we will go from there on being able to see how you would use your design. And so likely what will happen is I will do the examples, and then I'll give you some time in the class to work on your own designs within your groups, and then I'll be able to answer questions as they come up as you're working with your groups. All right, thank you guys for bearing with me on this, and I appreciate your willingness to let me do this video instead of being able to come to class on Thursday. And I hope you guys have a great week, and email me if you have any questions. And again, I'll be answering some of these questions that I'm sure came up while I was gone when I get back. So we will see you next Tuesday.